Okay, so welcome again. So today is the final talk of this series by Rajas. So he will be talking existence of higher extremal Kähler matrix on a minimal ruled surface. Yeah, over to you, Rajas.
Okay, thank you, Sachidanand, and also thanks to the organizers, Sandeep and Aritro. So, okay, so let me start with today's talk. So, this is going to be the final talk in this series. So, this series of talks was based on this research paper with the same title, Existence of Higher Extremal Kähler Matrix on a Minimal Ruled Surface. So, okay, let me begin with today's talk. So, in the last talk, I just briefly discussed about these notions of canonical Kähler matrix on compact Kähler manifold. So, if M is a compact Kähler manifold of complex dimension n, then we have some notions of Kähler matrix which satisfy some nice curvature related properties. So the most basic and fundamental among these canonical Kähler matrix are called as Kähler-Einstein matrix, which as we saw in the last class, these are simply Kähler matrix which satisfy the Einstein condition, meaning the Kähler matrix such that the underlying Riemannian metric is an Einstein metric. So the Ricci curvature tensor is directly proportional to the metric tensor. So these are Kähler-Einstein metrics. Then cscK metrics or constant scalar curvature Kähler metrics. So as the name suggests, these are simply Kähler metrics whose scalar curvature is a constant. So these are Kähler-Einstein and cscK metrics, and Kähler Kähler-Einstein metrics are special cases of cscK metrics. Then I discussed about these. I had discussed about these extremal Kähler metrics. So we had this Calabi functional, and then the Calabi functional was a real valued functional defined on the fixed Kähler class of the manifold, and then these extremal Kähler metrics are going to be the critical points of that Calabi functional. And we also saw the Euler-Lagrange characterization of extremal Kähler metrics. So that was uh, Kähler metric is extremal if and only if its 1,0 gradient is a holomorphic vector field. So okay, so these are the three well-known and classical notions of canonical Kähler metrics. These have been quite well studied, especially Kähler-Einstein metrics. The question of existence of Kähler-Einstein metrics on a general compact Kähler manifolds on a general compact Kähler manifold has been now completely answered with the resolution of the famous Yau-T and Donaldson conjecture. So okay, so for Kähler-Einstein metrics, I can just quickly tell what is the theory of these Kähler-Einstein metrics. So, uh, as the definition suggests, omega, if omega is a Kähler metric on this compact Kähler manifold M, then omega is Kähler-Einstein if the Ricci curvature form of omega, so Ricci of omega is equal to some lambda times omega, where maybe I can go to the previous slides to show the definition. Okay, so the definition of a Kähler-Einstein metric was that omega is said to be Kähler-Einstein if there exists a real constant lambda such that the Ricci curvature form of omega is equal to lambda times omega, and then the Ricci curvature form was a closed real 1,1 form which was defined by this expression. So and then this lambda is called as the Ricci curvature. So for these Kähler-Einstein metrics, the problem of the existence of a Kähler-Einstein metric on a general compact Kähler n manifold, that is clearly answered. So here we had also seen the notion of the first Chern class of a manifold, and this first Chern class is independent of the choice of the Kähler metric on the manifold. So this first Chern class. So there is a notion of positivity of the first Chern class, namely that so if a cohomology class can be represented by a positive can be represented by a Kähler form, then that cohomology class is said to be positive. And if that cohomology class can be represented by some form whose minus of that form is a Kähler form, then that cohomology class is said to be negative. And if a cohomology class is represented by the zero form, then it is said to be the zero cohomology class. So this C1 of M, the first Chern class of the manifold, we can have it to be either positive or negative or zero. Of course, there are also cases when it is neither, but suppose we are in these three cases, so then uh, the problem of the existence of these Kähler-Einstein matrix on a compact Kähler n manifold, on a compact Kähler n manifold, that says that if C1 of M, let us say C1 of M is negative, in that case, this scalar lambda which is there, the Ricci curvature, that will also turn out to be negative. So then if C1 of M is negative, we have something called as the Oba-Yau theorem. That theorem says that in every Kähler class which is proportional to C1 of M, there exists a Kähler-Einstein metric of negative Ricci. Yes.
No, I guess that was something else. So you can.
Sure. Okay. So the Oba-Yau theorem answers this question of existence of Kähler-Einstein matrix whose first Chern form is where the first Chern class of the underlying manifold is negative. And if the first Chern class is zero, then we have the Calabi-Yau theorem. So the Calabi-Yau theorem then says that in every Kähler class of the manifold, there exists a Kähler-Einstein metric whose Ricci curvature is zero. And metrics of curvature zero are called as flat metrics. So the Calabi-Yau theorem says that in every Kähler class of the manifold, there exists a Ricci flat Kähler metric. And then the most important question was when this first Chern class is positive, and that is called as the Fano case. So in that case, it turns out that not always there will exist a Kähler-Einstein metric of positive Ricci curvature, and there was a non-trivial obstruction to the existence of that, and that is called as the K stability. So that is some concept called as K stability. And then for this, in terms of this K stability, there was a formulation which was called as the famous Yau-Tian-Donaldson conjecture, YTD conjecture. So this Yau-Tian-Donaldson conjecture was saying that there exists a Kähler-Einstein metric in that Kähler class in the Fano case, like the case where C1 of M is positive. So there exists a Kähler-Einstein metric if and only if that class is K stable. So this was called as the Yau-Tian-Donaldson conjecture, which was unresolved for quite a lot of time. But then in 2015, this conjecture was resolved by Chen, Donaldson, and Sun, for which they got some award. I don't know whether it was Abel Prize or something, but they received an award for this. And then the Chen-Donaldson-Sun theorem proved the famous Yau-Tian-Donaldson conjecture. So this is just about these Kähler-Einstein metrics. So the theory of cscK metrics, meaning the question of existence of a cscK metric on a general compact Kähler manifold, is still unanswered, and for extremal Kähler metrics, it is even more so. Okay, so yeah, in these extremal Kähler metrics, in their definition, we had this Calabi functional, and we also had this Euler-Lagrange characterization of an extremal Kähler metric. Okay, so these are just some points to remember. And then the most important objects of this study are these higher extremal Kähler metrics. So for that, we had the higher Chern forms and higher Chern classes, and then the top Chern form is the one that we are interested in. So we write down this Cn of omega as the top Chern form. So this is a top dimensional form on the manifold, and then omega raised to the power n upon n factorial. So remember that omega is the Kähler form, so it is a 1 comma 1 form, means a 2 form. So then omega raised to the power n will be a real 2n dimensional form, so that will also be a top form. And it turns out that omega raised to the power n divided by n factorial is actually the volume form on the Kähler manifold. So we can have this expression like, because these are top dimensional forms, so there will exist a unique smooth function lambda from M to R, globally defined smooth function on the manifold, such that this equation is satisfied. Cn of omega is equal to lambda upon n factorial into 2 pi to the power n times omega to the power n. Then this lambda is called as the higher scalar curvature of omega, just by analogy with the equation for the scalar curvature. So and then we just take the analogy, and these two notions were defined by Professor Pingali. So omega is said to be higher cscK if this lambda is a constant, meaning the higher scalar curvature is a constant, and this is said to be higher extremal Kähler if its 1 comma 0 gradient is a holomorphic vector field. So okay, so the this was just a quick review of these 5 notions of canonical Kähler metrics. Now I will once again go back to the slides of today. Okay, so now I will start with the work which was uh, there in my research paper. So we are going to construct a surface. So this is a complex surface, meaning a manifold of complex dimension 2. So its real dimension is 4. So this is a ruled surface, which means that passing through every point, there exists a complex line, meaning a submanifold which is isomorphic to C. So okay, so first we start with a compact Riemann surface of genus 2, and then we can always construct a Kähler metric of constant scalar curvature -2 on it if we require the surface area to be 2 pi. So this follows from the Gauss-Bonnet theorem. So the Gauss-Bonnet theorem will give you that if we want the surface area of this metric to be 2 pi, then the scalar curvature, if it is a constant, then that will have to be equal to the Euler characteristic of sigma, and that in this case will be 2 minus 2g. The genus is 2, so it will be -2. So we can have this Kähler metric of constant scalar curvature on the Riemann surface, whose constant value of the scalar curvature is -2, and the surface area is 2 pi. So we have fixed this thing, sigma comma omega sigma, and then on sigma we have a holomorphic line bundle, and we have the notion of the degree of a line bundle, which is explained below. So this on sigma there is a holomorphic line bundle L, and we have a Hermitian metric on L, which is called as H, which we are calling as H. And then the curvature of this Hermitian metric, the curvature form, that is also going to be a 1 comma 1 form. So that curvature form is going to be minus of omega sigma. So it is a because omega sigma is a Kähler form, so this minus of that, so this will be a negatively curved line bundle. Okay, and then this script O is the trivial line bundle on sigma, and we take the direct sum, L direct sum script O, and we take the projectivization of this line bundle. So projectivization means that so this is a L direct sum O will be a rank 2 vector bundle. So in every fiber of that vector bundle will be a complex vector space of dimension 2. We simply take the projectivization of that. So this X is equal to the projectivization of L direct sum O, and then this X will be a it will turn out to be a compact complex surface, meaning a compact complex manifold of dimension 2. And then this is a ruled surface because we can check that this all the fibers will be biholomorphic to CP1, which is the complex projective line. So passing through every point, there is a complex projective line. So that's why it is called as a ruled surface. And this minimal thing, so this minimal is in the sense of complex geometry and not in the sense of Riemannian geometry. So minimal in the sense of complex geometry means that there is something called as the blow up construction in complex geometry. So given any complex manifold, we can construct another complex manifold from it by blowing up that complex manifold at a point. So and then the new manifold is called as the blow up of the original manifold at that point. Then a complex manifold is said to be minimal if it cannot be expressed as the blow up of any other complex manifold. So uh, meaning we also say it cannot be blown down further. So this surface X is minimal in the sense that it cannot be expressed as a blow up of some other complex two-dimensional manifold. Okay, so this is the minimal ruled surface which we are going to study. Fine. So maybe I can draw a picture of this minimal ruled surface. So before that, let C be any typical fiber of the minimal ruled surface. So because it is projectivization, so this typical fiber will be biholomorphic to CP1 or S2, the Riemann sphere. So every fiber is biholomorphic to the Riemann sphere, and then we have two divisors or hyperplanes, meaning complex submanifolds of codimension 1 of X, which are called as the infinity divisor and the zero divisor. So the zero divisor is simply the zero section of this line bundle. So the zero divisor will be simply a biholomorphic copy of the Riemann surface sigma, and then the infinity divisor is also a biholomorphic copy of sigma, but it is thought of as the copy of sigma sitting at infinity. So this can be explained by a picture. So we can think of this as a small section of the base Riemann surface sigma. So this is just a open subset of sigma. So sigma is a genus to a compact Riemann surface. So it is a complex curve. So we can think of this as a complex curve. And then at every point we have a biholomorphic copy of CP1 or S2, the Riemann sphere. So then so this the zero section can be thought of, the zero divisor can be thought of as just the biholomorphic copy of sigma sitting inside the surface X. So this is the zero section or the zero divisor, which we call as S naught. And then we also have another copy of sigma sitting at infinity. So it's like we are taking the projectivization to make the surface compact. So we have another copy of sigma sitting at infinity. And this copy is called as the infinity divisor, S infinity. So this is the compact complex surface X. So this is just the picture of this X. So we have the typical fiber uh, denoted by C, which is which are simply biholomorphic copies of the complex projective line CP1, and then the zero divisor is simply the zero section of the holomorphic line bundle L. So it is a biholomorphic copy of the base Riemann surface sigma, and we are taking the bundle projectivization. So we have another biholomorphic copy of the base Riemann surface sigma sitting at infinity, and we call that as the infinity divisor, S infinity. Okay. Okay, fine. So now we had the this zero and infinity divisors. So then we also have these intersection formulae. So the thing is that these C S infinity and S naught, their Poincare duals can be thought of as elements of the Dirham cohomology space H2 of x comma r, the dimension 2 Dirham cohomology space of X. So then we have these intersection formula given over here. So okay, and then I needed to explain what is the meaning of the degree of a line bundle. So just like we had the notion of first Chern class of a manifold, we can also define the notion of first Chern class of a line bundle, and then that is simply nothing but 1 upon 2 pi times the cohomology class of the curvature form of that line bundle. It is defined in exactly the same way as the first Chern class of a manifold. So the first Chern class of a manifold is then simply nothing but the first Chern class of the anti-canonical line bundle of the manifold. Fine. So the meaning of degree is simply this intersection number. So this square brackets sigma is the fundamental class of sigma, and then C1 of L uh, dot with the intersection number of C1 of L and sigma, that is called as the degree of the manifold. So this degree is required is going to be an integer because these are integral cohomology classes, and then this the value of this integer is called as the degree. So in this case it is degree -1, so this number is -1, and then uh, sigma, the Kähler class of sigma dot with the fundamental class of sigma, this is nothing but the surface this is nothing but the integral of omega sigma over sigma, and this integral is then by definition the area of sigma with respect to the metric omega sigma, and that is 2 pi. So these are the intersection formulae. These intersection formulae are required for identifying the Kähler class of the Kähler cone of the minimal ruled surface. Okay. Fine. Now we know that the Kähler cone of a manifold is the set of all cohomology classes is the set of all 1, 1 Dirham cohomology classes of the manifold, which can be represented by a Kähler form. So, so that is the definition of Kähler cone. And then we want to have a numerical characterization of the Kähler cone. So we had this typical fiber C of this projective bundle X, and then we had these S naught and S infinity. So the if we take the Poincare duals of C and S infinity, then by the Leray-Hirsch theorem, it can be checked that this second Dirham cohomology space H2 of XR can be written as the set of all real linear combinations of C and S infinity. So then if we take a general cohomology class, which is of the form A times C plus B times S infinity, which belongs to H11 of XR, the question is when is this going to be a Kähler class? Meaning when will it be representable by a Kähler form? And then the answer of this question, like this question was answered in the most general setting as well as in this particular setting by different people. So it turns out that this a times c plus b times s infinity, where a and b are any real numbers, given any such cohomology class, this will be a Kähler class if and only if these coefficients a and b are strictly positive. So that's why the Kähler cone of this minimal ruled surface X is precisely this thing in terms of its numerical characterization. It is the set of all a times c plus b times s infinity, where a and b both are strictly positive. Okay, so now that we know what is the Kähler cone of this minimal ruled surface, the task over here is now construct examples of these higher extremal Kähler metrics on this minimal ruled surface X belonging to different Kähler class of the surface. So fine. So for that, just a minute. So over here, we just do one thing. These scalar classes are of the form a times c plus b times s infinity. So what we do is that we take a, a to be equal to 2 pi and b to be equal to 2m pi, where m is any positive real number. So then the Kähler class becomes of the form 2 pi times c plus m into s infinity. So these this is just a subset of the Kähler cone, but it turns out that if we are able to uh, construct Kähler metrics of the required kind in these Kähler classes only, then we can simply scale those Kähler metrics, meaning we can multiply by k by 2 pi, which will give us the Kähler matrix belonging to these kinds of Kähler classes, k times c plus m into s infinity. And then these are precisely all the Kähler classes, meaning they exhaust the whole Kähler cone of X. So that's why we first construct the required kinds of Kähler matrix only in these Kähler classes, which are of the form 2 pi times c plus m into s infinity. And then we just apply a scaling argument to get our results in all the Kähler classes. So this just simplifies our problem. So our task is now to find a higher extremal Kähler metric omega on X, which belongs to this scalar class 2 pi times c plus m into s infinity. And so this higher extremal Kähler metric should be constructed by a certain method, which will be explained in the coming slides. That method is called as the momentum construction method, or the Calabi-Ansatz procedure. So we want to construct an omega which belongs to this scalar class 2 pi times c plus m into s infinity, and then it should be higher extremal Kähler. So by definition, these things should be satisfied. The second Chern form, which is the top Chern form in this case, that should be equal to lambda upon 2 into 2 pi square times omega square, where the 1 comma 0 gradient of lambda should be a holomorphic vector field. Okay, so now I will just explain briefly what this momentum construction method is. So this method is attributed to Hwang and Singer, and it improvises upon a certain thing which is called as Calabi-Ansatz. So, this Calabi-Ansatz was formulated by Calabi way back in 1976, but this momentum construction method is an improvisation of the Calabi-Ansatz procedure, and this momentum construction method appeared in the year 2002. Okay, so what we are trying to do is that we want to construct this metric omega on the surface X, but this surface X consists of these hypersurfaces, meaning codimension one submanifolds, which are C, S naught, and S infinity. So we can exploit the symmetry of this surface to construct this metric omega, and that is precisely what is known as Calabi symmetry or Calabi-Ansatz. So what we are trying to do is that we try to write down an ansatz for this scalar metric omega. So an ansatz is simply an equation or a statement in which we first write down the most basic form of it, and then we go on further to see what more conditions are needed for that thing to satisfy certain properties. So this omega is going to be given by this ansatz p star of omega sigma plus square root of minus 1 del bar of f of s. So this square root of minus 1 del bar of f of s, this should be reminding us about the del bar lemma, as well as about the definition of the Ricci form, because both of these things involve this square root of -1 del bar thing, and that is related to the fact that for Kähler manifolds, the Bott-Chen cohomology precisely agrees with the de Rham cohomology. Okay, so we are taking this bundle projectivization P, and we are pulling back omega sigma to X. So this P star of omega sigma is going to be a real 2 form on X. And then for this we are adding a certain term, and then this term is going to be deciding the Kähler class of this omega. So what we are doing is that we are taking this variable S to be the logarithm of the square of the fiber-wise norm on the total space of L induced by H. So remember that L was a holomorphic line bundle on sigma, and H was a Hermitian metric on L. So this Hermitian metric H will be inducing a norm on the fibers of L, and if we take the square of this fiber-wise norm and then take the logarithm of that, that coordinate is called as S. So that is defined in this way precisely. And then we have a strictly convex smooth function of S. So this f is a function from R to R, which is strictly convex, meaning f double prime is strictly positive, and S plus f of s is increasing. So 1 plus f prime has to be strictly positive. So we will see why these two conditions are needed, namely f is convex and s plus f is strictly increasing. So we have this ansatz for the Kähler metric omega, and we are claiming that we can construct the metric omega from this ansatz. So then it can be checked that for this ansatz to belong to the Kähler class 2 pi times c plus m into s infinity, this function f. So now we will see what additional conditions this function f has to satisfy. So we are already so now it can be checked that for this ansatz to belong to this Kähler class 2 pi times c plus m into s infinity, we must be having 0 is less than or equal to f prime of s is less than or equal to m. So this condition is just obtained by integrating this two-dimensional form omega over this s naught, s infinity, and c, which are going to be a complex codimension one submanifold. So their real dimension is also going to be 2. So this is we just integrate this omega over c, s naught, and s infinity, and we can obtain this condition. Okay, and fine. So the thing is that now that we have all of these conditions on this function f, with these conditions we define something called as the momentum profile, momentum variable, and momentum interval. So these are just some things which involve a change of variables, which is related to the Legendre transform. So like I'm just briefly describing this method. The details are given in the references which will be coming at the end of this these slides. Fine. So we have something called as the momentum variable first of all. So gamma is defined to be 1 plus f prime s, and then because f prime s belongs to the closed interval 0 comma m, so this gamma will be varying over closed 1 comma m plus 1, which is called as the momentum interval. And then this phi of gamma is defined to be f double prime of s. So because f is convex, so this f double prime is going to be strictly positive in the interior of this interval. Okay, and then we can check that these are then going to be the expressions for omega square and c2 of omega in terms of the momentum profile phi of gamma. And then we want this metric omega to be higher extremal Kähler. So for that, this expression needs to be satisfied. C2 of omega is equal to this thing, and then for that to happen, this lambda, the higher scalar curvature, that will be then given in terms of the momentum profile by this expression. So we can derive this expression by simply substituting both of these things in the second by substituting the first and the second equation in this third equation. So this is then the expression for the higher scalar curvature of omega in terms of the momentum profile phi of gamma. And now for this omega to be higher extremal Kähler, we require nabla 1 comma 0 of lambda to be a real holomorphic vector field. And then it turns out that if you equate these things, then lambda will be equal to some a times gamma plus b, where capital A and capital B are just some real constants. So then you will get this whole right hand side is equal to a times gamma plus b. Then bring gamma cube on the other side and integrate one more time. You will get another constant of integration, which is c. So then you get this ordinary differential equation. So this is the ODE which we will be getting, and then this there will be some boundary conditions on this phi of gamma as well, and these are precisely the boundary conditions. And because this phi was equal to f double prime, so phi should be strictly positive in the interior of the interval, and phi is equal to 0 at both the endpoints. So these conditions are required for the metric to extend smoothly across the 0 and infinity divisors. So remember that we are first constructing the metric only on x minus both the divisors, and then we are seeing what conditions are required to extend the metric smoothly across both the divisors.
Mm. Yeah, you are muted.
Yeah, got it. Yeah. Okay. So the main idea in this momentum construction is that it boils down the problem of finding this higher extremal Kähler metric to solving this ODE boundary value problem. So now the this problem which we had originally of finding a higher extremal Kähler metric omega, which belongs to the scalar class by the momentum construction method, that now boils down to solving this ODE boundary value problem for the momentum profile of that metric. So this ODE boundary value, this ODE is not directly integrable, as we can see, and that's why we cannot just directly solve it and then substitute the boundary conditions. So then some deeper analysis is required for getting the existence of a solution. So first note that this ODE has got uh, these three parameters a, b, and c, which are just any real parameters, and most importantly, it also depends on the parameter m, where m is strictly positive, and that determines this scalar class 2 pi times c plus m into s infinity. So m is the parameter which determines the Kähler class of the ansatz. Okay, so if we substitute these two boundary conditions in the ODE, we can get a and b as functions of c and m. So we have now reduced two parameters, namely these a and b. They are just going to be functions of c and m. So actually, we have only two independent parameters, c and m, with a and b depending on c and m. Fine. Then this polynomial we can simply denote it by p of gamma, and then we do a change of variables, which is v is equal to 2 gamma plus phi the whole square upon 2. And if we apply this change of variables on this ODE, then the ODE 1 will become the ODE 2 with these boundary conditions. So, so now this is the ODE boundary value problem with two independent parameters. So it now turns out that over here we have got four boundary conditions, two on V and two on V prime as well. But actually the thing is that these conditions on V prime are automatically going to be implied by the conditions on V. So V of 1 is equal to 2 is going to imply V prime of 1 is equal to 6, and similarly V of m plus 1 is equal to 2 times m plus 1 the whole square is going to imply V prime of m plus 1 is equal to 2 times m plus 1. So that's why we can simply remove these two boundary conditions on V prime. So then, so this is the lemma of Professor Pingali, who had first studied this problem. So from this, the ODE boundary value problem 2 reduces to this ODE boundary value problem 3. So we have this ODE on the interval 1 comma m plus 1, which satisfies these two boundary conditions. And then this ODE boundary value problem depends on the parameter m, which is going to decide the Kähler class of the ansatz, and also on the parameter c, which is any arbitrary real parameter. Okay, so I can then give a rough strategy of how to solve this ODE boundary value problem. So what we do is that in this boundary value problem, we simply drop the final boundary condition, namely the one at m plus 1, and we only consider the initial value problem. So then this is the ODE initial value problem. Then by Picard's existence and uniqueness theorem, every initial value problem, if the RHS is Lipschitz, then that will be having a, a solution locally in an neighborhood of 1. So by using Picard's existence and uniqueness theorem, we can then check that. So just yeah, okay. So now in this, the parameter m uh, that is being kept fixed, and we are varying the parameter c. So as we vary c, this boundary value, this initial value problem will also vary with the parameter c. So then for each value of the parameter c, there will exist a unique solution to this initial value problem in some non-degenerate neighborhood of 1. And then we have to carefully study the variation of this solution with respect to the parameter c. So the idea that we are using in the paper is that we had dropped this final boundary condition, and we are considering only the initial boundary condition, and then we study the variation of the solution of v with respect to the parameter c, and we want to find one value of the parameter c which does satisfy the correct final boundary condition. Okay, and I can just draw the graph of the solutions of these initial value problems. Fine. So on this interval 1 comma m plus 1, so the initial value problem was saying that v of 1 is equal to 2. So, and we had kept the parameter small m fixed, and we were varying the other independent parameter capital C, which is any real parameter. Okay, so the solutions to that ODE initial value problem then will be looking something like these. So they can have any value at the final endpoint. That is this v of m plus 1. We want it to be equal to 2 times m plus 1 the whole square, but that need not be in general. So let us say 2 times m plus 1 the whole square is somewhere over here. So we want v of m plus 1 to be equal to 2 times m plus 1 the whole square. So what we do is that we keep on changing the value of that parameter c, and then we are going to be getting different solutions v subscript c, which depend on that parameter c. So we get one value C1 for which V of m plus 1 is strictly greater than 2 times m plus 1 the whole square, and another value C2 for which it is strictly less than. So then by the intermediate value theorem, there will exist some value of C for which the correct final boundary condition is satisfied. So it actually turns out that this V subscript C, this is going to be monotone decreasing in C. So as we keep on increasing the value of the parameter C, these V subscript C, the they will keep on decreasing at every point. So then it keeps on decreasing, and then finally at some stage it hits zero. So this means that there should exist some stage in between where it should hit the value 2 times m plus 1 the whole square. So that is the whole idea of that analysis of the ODE boundary value problem. So like I'm not going to give the details of this proof. So this proof involves nothing more than elementary real analysis and also elementary ODE theory, like the Arzelà-Ascoli theorem and Dini's theorem. So, but it is a very long proof because we have to carefully get the estimates for proving that there exists a C which satisfies the correct final boundary condition. Okay, so this is what the strategy of attacking this ODE initial value problem is. So then, if we are able to solve
Rajas,
this
can you go
ODE,
to the previous slide once? Yeah. So here, like it might be elementary. I'm not understanding that. So this is a first order ordinary ODE.
yes.
So why we are given with the two boundary conditions or initial conditions?
Like these boundary conditions come from the problem. So like the thing is that this Kähler metric omega which we had constructed on which we wanted to construct on X. So this
Mhm.
momentum construction method, it first constructs it only away from the two divisors, the 0 and infinity divisors, and then it gives what conditions are required for this metric to extend smoothly across 0 and infinity divisors. So the thing is that these two boundary conditions,
Mm.
they are required for the metric omega to extend smoothly across S naught and S infinity. Otherwise, only by the momentum construction, it is just a smooth metric on X minus S naught union S infinity. But we want it to extend smoothly on the whole of X. So that's why these boundary conditions are coming.
So then by the so then we cannot apply the solution existence theorem here now because we have two initial conditions.
Yeah, so then after that, after doing this change of variables, that is
Huh?
precisely where this lemma comes, which says that this v of 1 equal to will automatically imply v prime of 1 is equal to 6, and v of m plus 1
Ah,
is
I
2
see.
times
Okay,
m
okay,
plus.
okay.
So that's why those conditions on v prime, they can be dropped, and we then are left only with the conditions on v.
Okay, okay, okay. Thank you.
Yeah. And then what we do is that we simply drop this final boundary condition and study only the initial value problem, and this initial value problem then depends on the parameter capital C. So we vary the value of this capital C, then we get different solutions to this this boundary value problem 4, and then these different solutions, they satisfy v of 1 equal to 2, but then they may not be satisfying v of m plus 1 is equal to 2 times m plus 1 the whole square. So we find one value C1 for which the value of v at m plus 1 is strictly greater than, and another C2 for which it is strictly less than. So then by the intermediate value theorem, there will exist some value of C for which the correct final boundary condition that we wanted, that is going to be satisfied. So this is like the whole idea of this solving this ODE boundary value problem.
Okay, okay. Thank you.
Yeah. Okay. So then the results in this say that as I told, so this problem was first studied by Professor Pingali, but he could answer this problem only in the case when small m is equal to 1. So only in the Kähler class 2 pi times c plus s infinity. So he could answer this problem only in that case, but the results in my paper say that this can be done for any small m positive, and that was a highly non-trivial thing, because the method that he had used in the case of m equal to 1, that used some specific estimates, whereas for getting the existence of a solution for any arbitrary m positive, that requires a deeper analysis of the variation of this initial value problem with respect to the parameter c. So then it turns out that we fix this small m positive, which is going to determine the Kähler class of the resulting ansatz. Then for depending on this small m, there first exists a capital M, which has value strictly greater than 2, such that if you look at this interval minus infinity comma capital M, all the values of the parameter c coming from this interval minus infinity comma m, for them this smooth solution will exist all the way till m plus 1. Like this smooth solution is going to exist in some neighborhood of 1, but it may not go all the way till m plus 1. But it turns out that for all the values of c coming from this interval uh, of parameters, the solution will exist all the way till small m plus 1. uh, and then if you take a value of c outside of this interval, then for them the solution will not exist till m plus 1, so it will break down before m plus 1. So then it has maximal interval of existence something like 1 comma gamma star c, where this gamma star c also depends on the parameter c. And then as I said, this v in terms of the parameter c, that is going to be decreasing. So if you so if you take c to minus infinity, then v of m plus 1 comma c will go to infinity, and if you take c to m, then v of m plus 1 comma c will go to 0. So this v of m plus 1, that takes all the values between 0 and infinity. So in particular it has to take the value 2 times m plus 1 the whole square. So that is then the idea that there exists a unique c is equal to c of m, which will belong to this interval of parameters, such that v of m plus 1 comma c is equal to 2 times m plus 1 the whole square. So this means that in this initial value problem, there exists a unique value of the parameter capital C which satisfies the correct final boundary condition, which means that we have solved this ODE boundary value problem 3. And then from this lemma, it means that we have solved this ODE boundary value problem 2, which then again means that we have solved this problem 1. So and then solving this ODE boundary value problem 1 was precisely equivalent to finding this uh, required kind of higher extremal Kähler metric omega. So like as is said over here, omega, this required kind of higher extremal Kähler metric, we can find it if and only if the momentum profile satisfies this ODE boundary value problem. Okay, so then these are the results, and then this result gives the existence of higher extremal Kähler metrics in each and every Kähler class of the manifold X. So this says that for every value of the parameter m, which characterizes the Kähler class, there exists a higher extremal Kähler metric omega, which has Calabi symmetry, which means which is constructed by the Calabi ansatz or the momentum construction, and which belongs to this Kähler class. And then this omega, if we multiply it by some k upon 2 pi, then k upon 2 pi times omega will belong to the Kähler class k times c plus m into s infinity. And the property of being higher extremal Kähler or higher cscK, or even extremal Kähler cscK Kähler-Einstein, all of these properties are invariant under scaling the metric by a positive constant, because the curvatures itself, they get scaled accordingly by that positive constant. So that's why if a metric is a higher extremal Kähler, then all of its positive scalar multiples are also going to be higher extremal Kählers. So that's why then this k upon 2 pi times omega will also be a higher extremal Kähler metric, which will belong to this Kähler class k times c plus m into s infinity. And then these Kähler classes precisely exhaust the whole Kähler cone of X. So that's why then for any Kähler class coming from the Kähler cone of X, there exists a higher extremal Kähler metric belonging to that Kähler class, which is constructed by the momentum construction. So this is then the final result that we have. Fine. So now to summarize, we have constructed higher extremal Kähler matrix in every Kähler class of the minimal ruled surface X by the momentum construction method. And now we know that all higher cscK metrics are going to be higher extremal Kähler, but the other way around need not be true. So then the question that arises is, are these momentum constructed metrics going to be higher cscK? And the answer for that question is no. So this question was answered partly by Professor Pingali. So Professor Pingali's theorem was that in any Kähler class of the minimal ruled surface, if we can construct a higher extremal Kähler metric by the momentum construction, then that higher extremal Kähler metric cannot be higher cscK. So he just answered that the higher extremal Kähler metric cannot be higher cscK given its existence. So the existence was not proven by him. But now if we combine our existence result with the result of Professor Pingali, we get this thing that in every Kähler class of the minimal ruled surface, there exists a non-higher cscK higher extremal Kähler metric, which is constructed by this Calabi symmetry method, and which belongs to that Kähler class. So okay, so this is then the final result that we are having, that we have constructed a higher extremal Kähler metrics which are not higher cscK in every Kähler class of the minimal ruled surface. And then the question now is of the existence of higher cscK matrix itself on this minimal ruled surface. So now note that the momentum constructed Kähler metrics are not higher cscK, but the question is, do higher cscK metrics even exist on the minimal ruled surface? And the answer to that question is no. And that question is then answered by using something called as the Bandow-Futaki invariant. So these Bandow-Futaki invariants are just generalizations of the Futaki invariant. So what these invariants do is that basically they provide obstruction to the existence of higher cscK metric in a given Kähler class. So as you can see from the formula, this Bandow-Futaki invariant, this Fn, so this is going to be a function from this set of all real holomorphic vector fields cross the Kähler cone. So this h of m is this h of x or h of m, that was the set of all holomorphic vector fields on the manifold. So we take that h of m cross the Kähler cone of the manifold. This Fn is going to be a function from h of m cross the Kähler cone of m going into the set of real numbers. And then it can be checked that this Fn is going to be a function only of the Kähler class. So it does not depend on the choice of the Kähler metric omega belonging to the Kähler class. And it also is not dependent on the choice of this form, this smooth form phi. So, okay, so this is then the definition of this Bandow-Futaki invariant. It is an invariant of the Kähler class. And what this Bandow-Futaki invariant does is that we can compute it on a Kähler class. If the answer turns out to be non-zero, then there cannot exist a higher cscK metric. Because if there exists a higher cscK metric, then the evaluation of this Bandow-Futaki invariant on that Kähler class has to be zero for every holomorphic vector field. So in this way, these Bandow-Futaki invariants, they just provide obstruction to the existence of higher cscK metrics. So these are, as I said, are generalizations of something called as the Futaki invariant. So that Futaki invariant is meant for cscK metric. So the theorem then is that if omega is a cscK metric, then the Futaki invariant is zero on that whole Kähler class. Oh, fine. So maybe then, so these are just some technical details about how you get to the result. So maybe I can just give the final results. So this in this theorem of Bandow, this is an if-then statement. We can make it if and only if this Kähler class contains a higher extremal Kähler metric. So if omega is a higher extremal Kähler metric, so then this class of omega is the Kähler class of a higher extremal Kähler metric. In that, in all such Kähler classes, this statement is going to be if and only if that the Bando-Futaki invariant vanishes on the Kähler class if and only if the metric is higher cscK. So from this we can see that suppose we are in the Kähler class of a higher cscK metric, and then if we take any higher extremal Kähler representative of that Kähler class, then that higher extremal Kähler representative also has to be higher cscK. From this second theorem, this corollary will quickly follow. Okay, and then now we saw uh, this result for our minimal ruled surface, which said that in every Kähler class there exists a higher extremal Kähler metric which is not higher cscK. So this is one result that we have, and then combine this result with the last corollary that we have here, that in a Kähler class in which higher cscK metrics do exist, in such a Kähler class, if we take any higher extremal Kähler metric, that also has to be higher cscK. So from these two things, we can quickly derive that higher cscK metrics do not exist at all on the minimal ruled surface X. So now we have proven these things over here, namely first that in every Kähler class of the minimal ruled surface, there exists a higher extremal Kähler metric which is not higher cscK. This is one thing that we have proven. The other thing is that higher cscK metrics do not exist at all on the minimal ruled surface. So the motivation for this problem was that, so as I said, these higher cscK and higher extremal Kähler metrics, they were defined by Professor Pingali by considering analogy with cscK and extremal Kähler metrics. So this same problem was studied in the extremal Kähler case as well. Namely, you take this minimal ruled surface X, you take this same minimal ruled surface X, and then you compute the Kähler cone of X, and then in this problem, instead of trying to find a higher extremal Kähler metric, they had tried to find an extremal Kähler metric. So the extremal Kähler equation will be that we have to take the first chain form in place of the second chain form. So over here it will be then C1 of omega will be equal to this C1 of omega wedge omega to the power n minus 1 equal to the scalar curvature of omega times omega raised to the power 2. So this lambda is the higher scalar curvature. In place of that lambda, we will be then having the usual scalar curvature. And then for the metric to be extremal Kähler, the 1,0 gradient of the scalar curvature should be a holomorphic vector field. And then this momentum construction method in that extremal Kähler case also gives a similar kind of ODE boundary value problem. But then the thing is, in that case, this ODE boundary, this ODE turns out to be integrable. So we can directly integrate that ODE and then substitute the boundary conditions. Whereas in this case, the ODE is not integrable. So that requires a very hard analysis for getting the existence of a solution satisfying all the boundary conditions. Okay, so this is one important difference between the extremal Kähler case and this higher extremal Kähler case. Another most important difference is in the result that we are getting. So the result that we get over here is that in every Kähler class there exists a higher extremal Kähler metric, but in the extremal Kähler case, the result was that this ODE boundary value problem actually cannot be solved for all values of the parameter small m. Meaning in all Kähler classes there don't exist there don't exist extremal Kähler metrics, but they exist only in some Kähler classes. So it turned out that there is some value k1 which is the root of some quartic polynomial. So k1 is the unique positive real root of some quartic polynomial, and then for 0 less than m less than k1, for those scalar classes there do exist extremal Kähler metrics belonging to this scalar class. But if we take m bigger than or equal to k1, then there don't exist any extremal Kähler metrics. So this result in the higher extremal Kähler case is in complete contrast to the result that was obtained in the extremal Kähler analog of this problem. Okay, and even in the extremal Kähler analog, they studied the Futaki invariant, which gives an obstruction to the existence of cscK matrix. So then in this theorem of Futaki, it said that if omega is csck, then the Futaki invariant on the Kähler class will identically vanish. And then over there also there was a similar theorem, namely if we are in the Kähler class of an extremal Kähler metric, then we can make this statement if and only if. So the Futaki invariant vanishes identically if and only if the metric is csck. So then, using the Futaki invariant, it was then proven that there don't exist any csck metrics on the uh, on the minimal root surface. So this is just a comparison of the results obtained in this higher extremal Kähler analog of the problem with the extremal Kähler case of the problem. Okay. And then these are just some references. So for these compact complex surfaces, so this is the book which can be referred for understanding what these intersection numbers. So like in the beginning, we saw these intersection formulae, like what are these intersection formulae, and then getting the notion of how the this Larey-Hirsch theorem, it numerically characterizes the Dirham cohomology spaces by the Poincaré duals of some uh, hypersurfaces of the manifold. So and then computing the Kähler cone by this expression for all of these things, this Bart, Hulek, Peters, Van Dieven. So this book can be referred on compact complex surfaces. And then yeah, the papers which are involved, the research papers which are involved in this are namely the extremal Kähler analog of this problem was studied first by C.W. Tönnissen Friedman, and this momentum construction method is given in the paper of Wang and Singer. And then these Futaki and Bando Futaki invariants, they are introduced in these two papers. And this problem of studying the higher extremal Kähler analog of this problem of C.W. Tönnissen Friedman, that was started by Professor Pingali, and that was completed in my paper. So these are some relevant research papers. And yeah, fine. Thank you.
Okay, thank you. So, any question? Okay. So, okay then. Yeah, thank you, Rajas. So, it was nice series. So, we hope to see you at some time. Okay,
Yeah,
see you.
I would like to. I would also like to thank all the organizers and all the audience for the organizers for inviting me for this seminar series, and the audience for attentively listening to my talk. Yeah,
Okay, so we'll meet on next Wednesday for another series. Okay, bye for that time.
yeah.